All right, now let's look at a problem that appears to be a bit more complicated. Some more problems involving dependent motion. To solve these types of problems, remember the basic idea. First thing to do, of course, is to establish a position coordinate measured from a fixed datum to each one of the blocks in the system. And secondly, you want to use geometry or trigonometry to relate the changing length of the chord that connects the blocks to each of the position coordinates. And in particular, if there are several chords in the system, then a position coordinate equation must be established for each chord. I'll solve a problem like this at the end of the lesson. And finally, you take the time derivatives of the position coordinate equation to obtain the relationships between the velocity and the accelerations of the blocks. All right, we'll begin with this one. Here we want to determine the velocity of block B when the cable A is being pulled upwards at 3 meters per second. So the first step, of course, is to set up our fixed datum. We'll put it right through here. From the datum, we have to locate the end of the cable at A, and we'll call that position coordinate S of A. Notice that it's positive when it goes downward. We also have to indicate the location of the block B. We use the coordinate going from the fixed datum down to the center of this pulley. Here it's S sub B. Positive downward again. If we know the position of this point, then through the geometry of all of this, we can locate B, of course. Now that the position coordinates are established, we have to relate them to the changing length of the cable. And that, of course, would be these 4 segments. Notice this segment of cable, along with the wrapped segments of cable around each of the pulleys, remains the same length for all time. But these segments here, along with this, when totaled up, is also equal to a constant value. It simply means that this segment will be getting longer, whereas these will be getting shorter, but the total length again will equal a constant value L. So let's write that total length. L is equal to, first we have 3 times S sub B, and then we have to get somehow this segment. Well, if you consider this total length to be h, a constant of course, then I can find the length of this segment, can't I? What would that be? You'd write it as plus h minus S sub A. Now that we have our position coordinate equation set up, we'll take our derivative. This, of course, is equal to 0. And over here we have 3 times V sub B. Then we have plus, this of course is 0. It doesn't change with time. And finally we have this term, minus V of A. And here if we solve for V sub B, we simply have it equal to V of A divided by 3. And so what would you put in for V of A? Well, I hope you would say minus 3, because the positive direction is downward. And so putting that in, we have minus 3 divided by 3. And of course that comes out to be minus 1 meter per second. What does a negative sign mean? Well, it simply means that B is not moving down in the positive S sub B direction, it's moving up. So we write it either with the negative sign, or we can put an arrow alongside the result to show what way it's going. We can also solve this problem in another manner, and let me show you how that would be done. We can consider a fixed datum placed down here at this point, and another fixed datum up here. If we did that, then measuring from each of these fixed datums to each of the points that we're looking at, for example, here we go up to A this way, where S sub A is positive upward. And then again for B, locating this point, we'll use an S sub B coordinate, which is positive downward. Now let's write the changing length of the cable in terms of our position coordinates. We have L equaling first 3 times S sub B, and we also have plus S sub A. Again, we don't put this length into our equation because it's constant for all time, along with the arc segments for each of the pulleys. Anyway, taking the time derivative of this, we'll get our velocity relationship. We have 0, and that's equal to 3 times V of B, and of course plus V of A. Now let's solve for V sub B. And doing so, we get the following: minus V of A divided by 3. We have to put in the data. We get minus. Now for V of A, what do we put in? Well, I hope you said positive 3, because it's in the direction of the positive coordinate S sub A. So putting in our 3 up here, and down below a 3 as well. So again, we get the answer that we had previously. In other words, minus 1 meter per second, telling us again that when A moves upward, B will be moving upward as well. All right, now let's look at a problem that appears to be a bit more complicated. But if we follow our procedure, we'll be able to get our answer in a pretty direct manner. Here we want to find the velocity of the block B when A is moving upward at 6 meters per second. So the first step, of course, is to set up our fixed datum. And we do that through this point right here, don't we? Now we have to locate the end of the chord. We'll use this coordinate S sub A, positive downward. Next, we also have to locate the block B. And the best way to do that is to use a position coordinate going to this point. In other words, we'll refer to this as S sub B, positive downward also. The reason I choose this point is because if I know the length of this link, I can locate B. Anyway, we have to relate our coordinates now to the total changing length of the cable, and that would be these 4 segments, wouldn't it? You see, as time passes, this segment right in here, this one, and this remain constant for all time. But these 4 segments, they all change their length. But the total length of all 4 is equal to our length L, which remains constant. So therefore we write L as equaling what? Well, you probably would say 3 times S sub B. And now we also need this piece. What would that be? Well, I hope you said it would be S sub B minus S sub A. Now that our position coordinate equation is established, we can take its time derivative and we'll relate our velocities. 0 is equal to 4 times V of B, and here we have minus V of A. Now let's solve for V of B. And when we do this, we get an answer of V of A divided by 4. Now we substitute V of A. And what would that be? Well, I hope you said it was minus 6, because it's going up instead of down. Dividing it by 4 will give us our result, and that turns out to be minus 1.5, and that of course is in meters per second. So here's our result, written this way, or you can also write it with an arrow going up. All right, here's our last problem. Here we want to determine the velocity of this block B when A is moving upward at 4 meters per second. Notice in this problem we have two cables in the system, one right in here, of course, and the other one which is going around here. But we solve the problem the same way we did the other ones. First step is to set up a fixed datum, and we'll put it through this fixed point up here, and from there we'll locate the position of A using this position coordinate to the center of the pulley. We'll refer to that, of course, as S sub A. B is located using this position coordinate, referred to as S sub B. Positive downward, just like S sub A. And finally, we need to locate the position of the end of this chord right here, and we use the position coordinate S sub C. Now that these are established, we have to relate them to the changing lengths of each of the cables. And so if we consider this cable, here's our changing lengths, just two of them. This piece up in here and the piece around here remain the same length for all time, but these two are changing their lengths. Therefore, we write that length as L equaling S sub A plus what? Well, I hope you said it would be S sub A minus S sub C. If I take the time derivative of this equation, I'll have a velocity relationship. 0 is equal to 2 times V of A minus V sub C. Now let's look at the other cable. Here, here, and here are the changing lengths. And again, the wrap up in here, around here, and also this piece remain the same for all time, but these three lengths will be changing with time. Total length L, of course, is constant. We'll call it L prime here. L prime is equal to 2 S sub C, and we have plus S sub B. Taking the time derivative of this equation gives us the following. 0 equaling 2 times V sub C, and we have plus V sub B. So essentially we've written two equations. And we want to express V of A in terms of V of B if we want to solve, because we know what V of A is. And to do that, you'll see up here that V sub C is equal to 2 VA. And if that's true, and I substitute it down here, I can write the following. 0 is equal to 4 times V of A. And we add to it V of B. And now I can solve. V of B is equal to minus 4 times V of A minus 4. Because obviously V of A is going upward. When you work this out, of course, you get your result. It turns out to be positive 16 meters per second. Indeed, block B will be moving downward at 16 meters per second when A moves up at 4 meters per second. And so having completed the problem, we'll end our lesson.